Welcome, and thank you for joining us. My name is Dean Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today we have the pleasure of presenting a public lecture by Christine Aidala and Gabriele Carcassi entitled 7 Misconceptions in the Foundations of Physics. Christine Aidala received her bachelor's degree in physics and music from Yale University in 1999 and her PhD in physics from Columbia University in 2005. After a postdoctoral position with the University of Massachusetts at Amherst, she was a Frederick Rhines Distinguished Postdoctoral Fellow and then staff scientist with Los Alamos National Laboratory until joining the faculty at the University of Michigan in 2012. In addition to her theoretical work on the foundations of physics, she performs experimental research in high-energy nuclear physics, studying the internal structure of the proton. Gabriele Carcassi received his degree in informatics engineering in 2000 from the Politecnico di Milano, Italy. He worked for 20 years in software and computing in support of large-scale accelerator facilities and experiments, from control systems and databases to wide-area network data management and security. For the past decade, he has had an increasing focus on foundational issues in physics, which he now pursues full-time. He has been a researcher in the physics department at the University of Michigan since 2012. He is particularly interested in the boundaries between foundations of physics, foundations of mathematics, and philosophy of science. If you have any questions during this talk, please type them into the chat or question and answer dialog box. At this time, it is my great pleasure to introduce Christine Aidala and Gabriele Carcassi.
Yes, thank you very much for the invitation to speak and for the kind introduction. Indeed, today we're going to be discussing 7 misconceptions in the foundations of physics that have become apparent to us over the last 8 years or so through work on our project, Assumptions of Physics. The broader project aims to identify a handful of physical starting points.
Wait a second, there is a small technical problem. There you go.
The aim of the overall Assumptions of Physics project is to identify a handful of physical starting points, so physical, not mathematical, from which the basic laws of physics, in principle, eventually across all the different established branches of physics, can be rigorously rederived. We have 2 approaches for the project, basically a top-down approach and a bottom-up approach. The top-down approach we call reverse physics. Now, for reverse physics, what we're really doing is we're taking some established branch of physics, say classical Hamiltonian mechanics, then we're reverse engineering, so to speak, the laws of physics within that branch of physics to try to identify a minimal set of physical principles from which the mathematical structures in that branch of physics can be rigorously rederived. So, for example, this is something we've done within classical Hamiltonian mechanics for the principle of least action. Our bottom-up approach, instead, we call it physical mathematics. In that, we are really creating mathematical structures from scratch. We are thinking about what the physical requirements are at very low levels, foundational levels, and then thinking what mathematical structures they necessitate. So as you'll see a brief example later in this talk, this is something we've done for the logic of experimentally verifiable statements and how this necessitates certain structures in point set topology. So it's really a project on it's about the foundations of physics, but it has overlap with some parts of the foundations of mathematics, as well as some overlap with philosophy of science. So, Gabriele, would you like to get us started about some of these misconceptions that we feel have come out through our work on this project?
Yes, so since people associate typically the foundations of physics with the interpretation of quantum mechanics, let's start from there. So the idea there is this sense in a lot of people that work on foundation that that's one of the key things to get right, to get the right interpretation. And like there are many issues of interpretation in quantum mechanics, but one of the most important one is the idea that you have two different ways that the state evolves in time. One is during a process, which is implemented through the Schrödinger equation, also called unitary evolution. And the idea is that given a single initial state, you get only one final output state, the final state. And this is what we use to essentially model all possible evolutions in time. This is also what people do in the standard model and in all our theories of physics. But the issue is that quantum mechanics also has another rule, which is used during measurement. And this is significantly different because while we do have one input state, the output can be multiple, and there is associated a probability with each of them. And so you have really these two different rules, and you need to apply them correctly in the different cases. And then there is the sense, of course, that any measurement at the end of the day needs to be a physical process. And so we would like to implement a measurement with a time evolution. And unfortunately, this is not possible, really, because these two things are very different. So the idea is that an interpretation would give us, let's say, what really happens during a measurement. It will tell us exactly what these states refer to, and it will tell us what happens during a measurement in terms of a time evolution of this more refined description. So this is where hidden variables or many word interpretation come in to really explain what happens during the measure. And now this is something very reasonable. Unfortunately, there is something that doesn't quite work. And the idea is that we use quantum mechanics not just for fundamental particles like an electron. We use them at different level of scale. We use them for a proton, which we know is not a prime object, it's made of quarks and gluon. We also use them for an atom, or we even use them for big molecule like a buckyball, which basically looks like a soccer ball. And so the idea that in the appropriate condition, all these at different scales, they get modeled with the same set of equation and the same measurement processes. And now, if we really wanted to have sort of a lower level explanation of this, one wouldn't suffice. We have to say in L level of scales what is really happening. And then, even worse, we would have to explain why all these four different things, actually there are many, many different things, at all different levels of scales, the model is exactly the same and follows the same rules. So it's unlikely that we're going to find one true mechanism that's playing all these different things that work within the scale. And so the question is, why is it that there is so much focus on these type of interpretations?
Well, most of the business of physics, what we do as physicists, is about mechanisms. So physics explains the behavior of a physical system in terms of its constituents and how those constituents behave and interact. And so if I think at macro scales, so if I want to describe water flowing in a river or through a pipe, I'm treating water as a continuous fluid, continuous matter. I use continuous equations. I don't worry about any substructure, but if I want to have a more detailed description, we know that we can describe water in terms of water molecules. Those in turn can be described in terms of hydrogen and oxygen atoms. And then I need to talk about the chemistry of the chemical bonds and different levels of interaction. I can go down yet further in physics and talk about the structure of those atoms in terms of the nuclei and the electron. I'll need quantum mechanics now, which I certainly didn't need to use when I was talking about water flowing in a river. But if I want to talk about those constituents at these more and more refined levels, I'm going to need quantum mechanics, talking about the electron energy levels of the atoms. Of course, we know that the neutrons and the protons are not fundamental particles either. They're made up of quarks. And so we considered it really the business of physics, and it certainly is a big part of the business of physics, to understand the constituents of matter and how they behave. But if we really want to get to the most fundamental level, this reductionist approach clearly has to stop somewhere. It's not going to work forever. And so in a fundamental theory, the objects cannot be further decomposed, right? That's what makes it fundamental in some sense. So we're going to need some kind of alternative way of framing this, of looking at the problems. Well, if it's not going to be about behavior at this fundamental level, we can try to consider the properties of processes. So not how they happen, but the requirements that different types of physical processes must have. So any process, deterministic or stochastic, will take a statistical ensemble as input and return a statistical ensemble as output. So none of our experimental manipulations or measurements have infinite precision. We also want to be doing things many times to perform experimental measurements. And so we're effectively taking some kind of input ensemble. Here I've described it as a distribution rho, I for input, undergoing some process, and then I have some output distribution, output ensemble. Okay, so what are the properties of ensembles if I'm going to look at things this way? Well, statistical ensembles can be mixed. So I can take two different statistical ensembles, combine them with different probabilities, P1 and P2 here, and get a mixed ensemble that is the combination of these two other ensembles. And then in terms of properties of ensembles, I know that the output of a mixture must be equal to the mixture of the output, so that I'm going to have something that's linear in probability. Okay, well, now let's consider two different types of processes. So if I have a process that happens to be deterministic and reversible, or is well approximated as deterministic and reversible, what I mean here by deterministic is that I have a one-to-one map between the state at the present time and the state at some future time. Sorry, I have a map going straight from that. The fact that it's reversible means it's a one-to-one map. So reversible means that I can, if I know the state at the present time, I can reconstruct what it was at some previous time. So if I have a process that's well described as deterministic and reversible, then it must conserve probability and it must allow an inverse. Now, this would correspond mathematically to a unitary operation. If I have a measurement process, well, what we want, if we're doing measurements in physics, we want them to be repeatable. Otherwise, it's really not a well-constructed measurement. So it means if I perform the same process on it twice, I should get the same output. Mathematically, this would be known as idempotent. It's also linear. So in mathematics, an idempotent linear process is known as a projection. So it shouldn't be surprising to us that what we consider measurements in physics actually are mathematical projections. So the difference in behavior between these two types of processes, right, it's really intrinsic to the definitions of what a deterministic and reversible process is and what a measurement process is. So any processes that approximately satisfy the requirements of either a deterministic and reversible process or a measurement process, and just the two examples I've given here, will do. I don't need a particular mechanism to say, oh, well, what's going on that makes it deterministic and reversible? What's going on that makes it a measurement? If it satisfies the definition of deterministic and reversible, or if it satisfies the definition of a measurement, then it's going to have certain properties. So why aren't these types of definitional explanations or considerations more prominent in physics?
Well, there is a sense in physics that what we describe through the laws of physics are really the laws of the universe. So that the goal of physics is fundamentally to understand what are the ultimate constituents of the universe and how they behave. And the mathematical objects represent real entity in the world. But before, by looking and applying the same model at different level scales, of course, that's not what we are doing. We're implicitly assumed that a physicist produces an approximate model that we are going to implement in different circumstances. And moreover, the underlying assumption is that these models have to be only about the part of the universe that is experimentally and empirically accessible in a systematic way, right? So there is sort of this contrast between two views of what the laws of physics are, and then we want to understand, well, which one is the correct one? Which one should we take? And one of the things that we do in our project Assumption of Physics, one of the results is part of physical mathematics. We can start from scratch with the notion of a verifiable statement. That is an assertion that can be experimentally verified in a finite time. That is, we have a statement S1, and we have associated a test. And if the statement is true, and only if the statement is true, then the test will always succeed in a final time. So, for example, the mass of the photon is less than 10 to the minus 13 electron volt. That's an actual thing that we can test experimentally, and we know it to be true because we created an experiment that measured the mass of the photon to that level of precision. But the statement, the mass of the photon is exactly zero, that's never something that we're going to be verifying, because we can't verify things at an infinite precision. That answer is never something that we can reach experimentally. So the idea is then that we should look at the logic of these verifiable statements, and we find that they don't quite follow the same logical rule. You can't implement the same rule on top of verifiable statement that you would on normal statement. And one of the key reasons is that because you have this issue of non-termination. So if your test doesn't happen to terminate all the time when the statement is false, if you implement a negation, for example, then now your test wouldn't be guaranteed to terminate every time that the statement is true. So you do not have a negation. You can have the finite conjunction, the logical end, right? So statement one and a statement true the overall is true if all the elements are true. And what you can do is simply test every statement independently, and they all turn out to be true. They will turn out to be true in finite time, and therefore your logical end is going to be verified in finite time. And of course, you're not going to be able to do a conjunction over infinitely many statements because it would require an infinite amount of time. That's something that you would be able to do on a normal statement, but you can't do it if you want your statements to be verifiable. If you consider instead the disjunction, the or, at that point the logical or is going to be true only if you just need one statement to be true. So as long as you verify one statement in finite time, you are done, and you can quit your procedure. So if you have even countably many, infinitely many statements, as long as you find one that terminates, you can terminate, and you're good. And so you have this, you don't have the negation, you have the finite end, you have the countable or, and these rules, actually what happens is that they map and recover a fundamental mathematical structure known as topologies and sigma algebras. And these are the fundamental mathematical structure on which everything else we use in physics is built. So all of our notion of geometry, differential geometry, and so on is built on the topology. All our notion of measure theory, probability theory, information theory is built on the sigma algebra. So the idea is really that this layer that is there put by mathematician actually performs a role in a physical theory, which is to keep track of which statements are verifiable and which are not verifiable in the physical theory. So we can also, in our work, we go one step further, and we also find a set of idealized assumptions on our verifiable statement that tells us in which conditions we can actually model real value of quantities. And of course, we find that these statements are very highly idealized, and you wouldn't think that these are doable in practice. But again, in certain contexts, we can make that approximation, pretend that we can make statements of arbitrary precision and always being able to measure that as an arbitrary small precision as we want. And under those assumptions, we can get and we can recover the idea of real continuous quantities. So the picture that comes out then is that if we want, we can say that there is a metaphysical reality, things that philosophers are mostly interested in, what really exists. But the physical physical reality, the one that we can actually study experimentally, is smaller and it has more constraint, right? You need to have these tests. These tests follow certain rules that are more restrictive than what can really exist. And the physical theory is really an idealized account of the physical reality. So really, if we really want to have a good understanding of our physical theory, we must understand what happens during within this border and within this step. And so if we say that the physical theory are models based on idealized verifiable statement, well, we can say that this is the correct viewpoint in the sense that it's more fruitful because it gives us the correct mathematical structure. And so we've seen essentially that the most basic mathematical structure, topologies and sigma algebra, can be derived through simple reasoning about empirical models. And there is nothing that we said here that couldn't have been developed 80, 100 years ago when mathematicians and computer science were thinking about issues of finite time termination and the finite symbol manipulation and so on. So this sort of brings up the question, why don't we have already a theory that tells us these things?
Well, the laws of physics are found experimentally. We needed another 80 years of experimental studies and new phenomena. They're not found by sitting down in your chair and just thinking about how things must be, right? So the idea that we can sit and think and determine scientific truth, many people would consider preposterous. And Galileo, many people think Galileo found out that objects fall at the same rate through experimentation, not reasoning. Well, we can do a thought experiment about things falling and how quickly they fall. So we can start by supposing that heavier objects fall faster than lighter ones. And then we can think about connecting a heavier object with a lighter and how that's going to impact the motion. Well, if a heavier object is falling faster and the lighter one is falling more slowly, now if I combine them together, attach them somehow, the slower object's going to slow the faster object and vice versa. It should go with some rate in between. The combined object should fall more slowly than the heavier part did by itself, would be what I'd conclude. But I would also conclude that the combined object must, of course, heavier than the heavier part alone. And I said that heavier objects fall faster than lighter ones. That was my initial supposition. So therefore, the combined object must move faster than the single heavier object, not slower than the single heavier object. So this leads me to a contradiction. And therefore, just by doing this kind of thought experiment, I can conclude very robustly, right, that heavier objects cannot fall faster than lighter ones. And we reach this conclusion in a really strong way. We don't have to worry about uncertainties on the measurement, friction through the air drag and things like this. And in fact, that is exactly what Galileo did. Stories of dropping things off of the Leaning Tower of Pisa to the contrary. And here is a quote in the original Italian and translation into English from his dialogues. And you can just look at the end here where the characters are discussing the motion of falling bodies of different weights. Now you see then how from supposing that the heavier object moves faster than the lighter, I can conclude that the heavier moves more slowly. So he gets to this contradiction through a thought experiment. And of course, we're not saying by any means that we're going to throw experiments out the window. The experiments are fundamental to all of science, but you can get a lot farther than you might think with these kinds of lines of reasoning. And we're not so much thinking about sitting in your chair and imagining all the different possible ways the world could be and trying to write down theories from them. We're thinking at a more a simpler level in some sense, or a more foundational level of what kinds of physical principles or mathematical structures are necessitated by these very simple lines of reasoning. So can we find other lines of reasoning to justify other physical ideas? Well, in classical mechanics, states are defined by position and conjugate momentum. So I'm going to talk here about a result from our reverse physics approach applied to classical mechanics. So yes, in classical mechanics, states are defined by position and conjugate momentum. Well, in statistical mechanics, the count of configurations, the number of different configurations, physical configurations of my system, is given by areas of position and conjugate momentum. And conjugate momentum is expressed in inverse units of position. So if I'm expressing my position in terms of meters, and I have some region in position, region in physical space, that's 1 meter here. Conjugate momentum is expressed in joule seconds per inverse meter. So it's going to be related to an inverse position coordinate that's tied to my choice of the position coordinate. So the product of position and momentum, when I have this conjugate variable structure, does not depend on the choice of frame. So the count of states is going to be frame invariant. And this is something I want, so that we should have an objective count of states. It shouldn't matter the frame that I'm doing my calculation in. If somebody else is doing a calculation in a different frame of reference, that they count a different number of states or number of configurations of the system. But it should be a fixed number of configurations, a fixed number of states that we objectively agree on. So if I do a coordinate transformation and instead of using meters, I use centimeters. So the same length region that is 1 meter, I would now express this as 100 centimeters. So again, numerically, if I'm just telling you something, counting the number of states, okay, now I'm expressing the same physical distance with 1 unit or 100 units in the 2 different cases, my different choice of units. But using this conjugate variable, now I'm going to have to express it in terms of inverse centimeters, and it gets scaled correspondingly by a factor of 1 over 100. And so in both cases, whether I'm using 1 meter as my or 1 meters as my reference unit or centimeters as my reference unit, when I take the product of the position and the region in position, the region in conjugate momentum, I'm going to get 1 unit of area. Just by requiring the count of states to be frame invariant, so this immediately tells me that states must be described somehow by some kind of conjugate pairs, like position and conjugate momentum in the case of classical mechanics. So classical states must be defined by position and conjugate momentum, because this is the only way that we can define state count. Entropy is going to be related to this, probability densities, determinism and reversibility is going to conserve this state count as we make 1-to-1 maps with the number of states in an area of phase space at a certain time or a future time, or reconstruct what it was at a past time. It's also linked to information theory, information entropy. Defining states with these conjugate pairs that lets us calculate all these things in a way that's objective and the same for all. So in the same way that we concluded just from reasoning that objects must fall at the same rate, states must be defined by conjugate pairs. So looking at the math closely, we can find in many cases, more cases than you might think, we can find conceptual reasons for a lot of physics. So why isn't this type of approach pursued more?
Well, probably because you have to look at the math closely. And in physics, we often think that the mathematical details are for mathematicians to worry about, and that there is no physics inside. I mean, mathematics is full of technicalities that are uninteresting to physics, and it's the job of the mathematician to take care of those technicalities and to find the correct framework and fix the details. And this is a reasonable things to think, because that's what we do for almost any other any other subject in physics, right? Whenever we create an experiment, the mechanical detail of what type of support we need and so on will be taken care by the mechanical engineer, or the electronics by the electronics engineer, and the software we might consult with the software engineers if we need them. And all these people are going to go and take care of those details that are going to be most of the time irrelevant to the experimental setup. But the difference here is that mathematics plays a much bigger role in our physical theory than mechanical engineering, the software engineer have for an experiment, because mathematics is not just a tool for calculation. It is the language that we use to formalize our physical models. In fact, a lot of the current more modern theory are just formalized in terms of a mathematical postulate or equations. They don't even have some like physical starting point to justify the mathematics like we had for the laws of thermodynamics or the laws of motion for Newton. So the issue is that how can we expect mathematicians who are really typically not trained in physics to know what are the correct features of our physical model? And quite frankly, I had this this assumption was so ingrained in my head that, you know, it's mathematician's job to give us the correct models, that only when during a topology conference, I was chatting with a mathematician and sort of expressing my frustration, and sometimes, you know, that the mathematics was not quite exactly, was too abstract. He basically said, yeah, I don't know the physics. I can't help you. You have to tell me what your requirements are. And so, as an example, in quantum mechanics, physical states for quantum states are modeled with array in a Hilbert space, which is some type of mathematical structure, and observable, like things that we actually measure, like position, momentum, and so on, are modeled by Hermitian operators, which is some other type of mathematical structure. And then the math tells us through a theorem that unbounded operators cannot be defined on the whole Hilbert space. And this is, of course, a mathematical thing. But what does it mean in terms of the modeling that we have? Well, it means that there exists some state for which some quantity like position, momentum, energy, number of particles is infinite or not defined. So the expectation, or let's say position of energy or energy for a particular state is going to be infinite, and which of course does not make sense for us, because how would we be able to produce a state that has infinite energy, or measure a state for which the average position is undefined? Where would we put the detector, right? It doesn't make sense. So mathematical details are physically important, and the mathematical definitions are there to capture physical requirements. They're not there to solve some mathematical problem. They're there to express in a formal language what is it that we're trying to describe physically. And so the fact that we don't know, that we sort of gave up on this enterprise and we just let the mathematician doing it, it's a problem for physics, because we're not going to end up with the correct mathematical structure. So ideally, right, like we have a part of the physics community that works to define units and how to define these things as best as possible, and what is the correct definition. How do you structure these definitions, right? There is a community of people that are very technical, that go and solve those problems, and then the rest of the physics community just use those things as inputs. It would be reasonable to have part of the physics community specifically working on developing physically and mathematically sound tool, going through all these details of these mathematical definitions and see and question whether these are the correct definition for what we need to do in physics. What is it that we have to do in physics such that we need to put them in the mathematical definition and so on. But unfortunately, we don't do that. And again, it would be something very reasonable. So why is it that we don't do that?
Well, there's only one correct way to do mathematics. The mathematician should find it, right? 1 + 1 is always equal to 2. In the same way that there are correct laws of physics, there's correct math, right? So mathematicians, they're dedicating themselves to mathematics. So if there's only one correct way to do math, then mathematicians had better be doing correct math, right? They'll discover the correct structures, organize them, and they'll be able to take prototype theories from us physicists and then give us the correct mathematical structure, right? If there is only one way to do mathematics, then the mathematicians better be doing it. But in reality, mathematics as a discipline is based on axioms and definitions chosen based on specific goals, the goals of mathematicians, naturally enough, because they're the ones developing this. There's something known as the axiom of choice in mathematics, which says that given any collection of sets, including infinite collections of sets, you can pick one element from each set. And there are mathematicians who accept the axiom of choice and who reject the axiom of choice. So again, there isn't just among mathematicians, mathematicians themselves don't have just one way to do mathematics. So mathematicians who accept the axiom of choice are effectively accepting anything that can be formally defined, regardless of whether or not you can write down an example of it. So they admit they're interested in studying the existence of objects that cannot, studying objects that cannot be written down with finitely many symbols. For example, one example of this is something known as the well-ordering of the reals, which says that there exists a different way of ordering the real numbers, so not the standard one that we're all familiar with, such that every real number has an immediate real number after it, right? And an immediate successor. And mathematicians who do this, there's a way to define it, allow it to exist, but there's no way to write it down. If you say, okay, well, here's a real number, tell me the number that is the immediate successor of it, and you can't actually give an example. So mathematicians who reject the axiom choice would say that this is nonsense. What does it mean that if you can't give me an example of something, you think it's interesting to study? So mathematicians who reject the axiom of choice are only interested in what can be constructed or computed, sometimes called constructivist mathematicians. But this would lead us, thinking as a physicist, this would lead us to the non-existence of objects that we find useful in physics, like the real numbers. In physics, we don't really fit with either of these choices, right? These aren't the kinds of things we're interested in thinking about. We care instead about what can be experimentally identified. And so already we see within mathematics as a discipline that there is more than one correct way to do mathematics. But then on top of that, the one that we physicists are interested in may or may not be one that mathematicians care about for any given branch of mathematics. So where does this leave us?
Okay, so we've seen sort of a number of ideas that we have in physics that after a little bit of more scrutiny, you basically see that there are some problems with it. And there is another one to conclude, the last one, is the idea that a theory of everything is the right foundation for physics, right? So a lot of the work in the foundation physics is essentially finding a theory that puts together quantum mechanics with relativity and tries to solve this issue. Now, of course, this is something that we want in physics. The issue is that it's seen as the solution of the foundation physics. That's the thing that we need to really know what's going on in our physical theory and what our physical theories are, and have a complete picture. And the issue is that from our perspective, this is actually thinking that the theory of everything is the right foundation of physics, sort of implicitly uses some of the things that we had before. So the idea that the theory of everything will fix everything is because in some fashion, you're thinking that a theory of everything will tell us what happens during measurement in terms of some mechanism, right? Describing the most fundamental objects on the universe and how they behave. And since the correct theory is determined experimentally, we should just focus on building rough prototypes to get something that we can go and look, because in the end, the mathematical details is irrelevant, and the mathematician will later find the correct formulation. And so from my perspective, even if we had a theory of everything, we still would have all the other problems that we said before, because we still have the question of what is the right mathematics, what are these models, what are the requirements for this model, and how do these things come about. And so if it's our belief that a theory of everything is not going to solve the foundations of physics, then the question is, what should the foundations of physics be about? And to do that, to answer this question, we should just look at what other disciplines are doing and get ideas from there. So in the foundations of mathematics, the foundations of mathematics define the basic objects and the rules that are always used to do mathematics. So mathematical logic is going to tell you the rules of logic, and set theory are the rules for the sort of the most basic constituent of mathematics, and everything else you can build it from there. And the foundations of mathematics also give a formal framework for what can be achieved in mathematics. So you have proof theory, and proof theory studies what can be proved from a set of axioms and what are the limitations of that. And in fact, this gives us limits in mathematics, and the Gödel's theorems, for example, tells us that every system that is complex enough, a system of axioms that is complex enough to describe the natural number will contain statements that are not proved. Now, if we look at the foundations of computer science, there is something similar. They define the basic objects and the rules to perform a computation, to describe algorithm in terms of symbols. And you're going to have a theory of computation, you're going to have information theory that sort of tells us, define these basic objects and state the basic rules of these objects. And they give a formal framework for what can be achieved by a computer. You have the complexity theory that tells us there are different problems that can be solved by different algorithms, and not all algorithms have the same complexity, and some of them might actually not be solved efficiently by computers. And this also puts limits on what computer science can do. For example, we know that there is no general algorithm to determine whether a program will terminate or not. So if somebody tells you, oh yes, I'm going to write a program to make sure that all other products program functions correctly, well, that's something that we can't do in computer science, because there is a theorem that tells us that we cannot do it. And so what we should have for foundations of physics, well, we believe that we should have something similar. We should have something that defines the basic objects and the basic rule that characterize physical systems and physical theory, and give a formal framework for what can be achieved through experimentation and how to formalize that. And maybe that is going to give us some limits on physics, in the same way that there are good foundations for mathematics and computer science gave to those disciplines. So this essentially tells us that we have a very sort of alternative, different approach for the foundations of physics. As you said, a lot of people are looking for a theory of everything. And if you have this idea and you want this as a foundation of physics, what you note is that all the other theories, right, general relativity is going to be just an approximation of the theory of everything in particular circumstances. And what happens that you just go through approximation. So all the objects that you define in the theory of everything are not there in the other theories. And that's sort of the problem. That's why this wouldn't solve the problem of foundation of all the other theory, because we just have approximation. Another particular approach for foundations of physics, especially more on the philosophy side, is construct interpretation of the physical theory that we have right now, like quantum mechanics, general relativity, and so on. In our approach, really, we want to find a minimal set of physical assumptions from which you can derive the law. And so the idea is to have first some general principle and requirements that all physical theory should satisfy to be called physical theories. And this should give us a general mathematical framework that is always valid in all other theories, in the same way that in mathematics you have set theory, and all other structures in mathematics are sets with some additional structure. So everything that you prove in set theory is valid in group theory, in topology, and so on. So that layer gives a common language to all the branches of mathematics. And this is not something that we have in physics. We have some sort of notion of state, for example, but the way that state is defined in all the different theories is completely different and very disconnected. And that's where we have problems of interpretation, because we don't know how those things relate. And so to give a little bit more of an idea of the detail of how our frameworks we think can work and how foundational theory can work, as I said before, we should have a general theory with all the basic requirements and definition that are valid in our theory. as we said before, experimental verification is important. And so we are going to have a layer that guarantees that there are verifiable statements and that the whole theory, the whole physical theory, can be generated in some mathematical sense from those statements. And that leads us to topologies and sigma algebras, which are essentially the foundational layer for all the other geometrical, probabilistic, and all the other structures that we have. Then we believe that there should be another layer that talks about how much information each statement brings in, so that we can create all the major theoretic, probabilistic, and geometrical level that would be satisfied, would be given by this layer. And then we should have a general idea of what states and processes are, so that we have abstract definitions that are literally always valid in all physical theory, so that we can, as I said, build a foundation that is common for all of them. And then if we did that, then we would have the space of all well-posed physical theories, which we could give to a mathematician, and then they can tell us, oh, these are the type of things that you can have or you cannot have. But then physically, what we are interested in is defining assumptions. So for example, we can say that we have a system that it's made of parts and the parts are made of parts and so on. And therefore, describing the whole system is equivalent to describing all the state of this infinitesimal part. And in this case, we can show that we can recover the classical phase space, the state space for classical mechanics. Similarly, we want to make a different assumption. We say that the system is irreducible. It can't be studied further. So, for example, if we have an electron, right, we can't make an electron interact, make a photon only interact with some part of an electron. When we interact with the electron, we interact with the whole thing. So we can't reduce and see more what's inside. And we believe that through some mathematics, you can show that you recover the state of quantum systems. And these are assumptions on the state that further refine the state, and you can have an assumption on a process. If you say that the process is deterministic and reversible, then this is going to give us a set of other, a smaller set of physical theory, and the intersection between these two sets of theories recovers Hamiltonian mechanics, and the intersection between these two sets of theory recovers quantum mechanics with the standard Schrödinger evolution. So this is sort of at a high level what we are looking for in the foundations of physics. And so the final take-home message is that we believe that we can give physics a more mathematically precise, conceptually consistent, and physically meaningful foundation if we, of course, overcome the misconception that we have seen. So thank you all of you for your attention.
Thank you very much, Christine. Thank you very much, Gabriele. That was a very thought-provoking and interesting discussion. There were a few questions I can go back to now. So Catherine Hunt had a few questions, but I'll just go in order of how things were asked. How do I know that if a smaller falling object is attached to a faster falling object, it will actually slow the faster object? This seems to me like an assumption. I might hypothesize that the combined object would fall even faster.
Yes, so that is, you can reason and lead to both conclusions. That if you attach a slower object to a lighter object to a heavier one, and you said that the lighter object was moving more slowly, if you just think of attaching something slower to something faster, it should slow it down, right? By the fact that you attached something that was moving slower. But the other conclusion that you necessarily reach is that the combined object is heavier, and therefore, if the supposition is that heavier objects fall faster, you reach that conclusion as well, and that's where the contradiction comes in. I don't know if that's a satisfying answer or not.
Yeah, I think that works. Okay, so there's a question for the statistical mechanics example. Are two frames that differ only in the units used to measure length really different frames?
Do you want to?
Yeah, there are different frames in the sense you're using a different set of coordinates. So if you want to say that those are the same frame with just different units, then you're just making the argument stronger, because you're saying, oh, I'm in the same frame and now I change units and now my count of state is different. So In our mind, the frame is also defined by the variables and the units that you are using, and this is sort of what happens then when you do it relativistically. But I mean, if you want to argue that there is the same frame, you still have the same problem, that if you're using the same frame, your count of states should be the same regardless of the units and coordinates that you've chosen.
Okay, thank you. All right, so another question from Catherine Hunt. My understanding is that the axiom of choice implies the Banach-Tarski paradox, which says that a solid ball in 3 dimensions can be decomposed into a finite number of disjoint subsets and then can be put back together to yield 2 identical copies of the original ball. Do you rule that out on intuitive physical grounds, or do you accept it?
It gets ruled out by the fact that we recover the correct sigma algebra. So the Banach-Tarski paradox requires you encountering when you're trying to put a measure, let's say a volume size, on all the possible set, let's say, of a 3-dimensional space. And inside those sets, there are a lot of things that sort of make absolutely no mathematical sense. No physical sense. They make mathematical sense, but at least for the, if you assume the axiom of choice. What happens is that in physics and normally even in mathematics, when you put measure, you don't put a measure to the full set of subsets of the 3-dimensional space. You only put it on top of what are called the Borel sets. Now, in our derivation, what happens is that the Borel sets are exactly those volumes that you can associate a test for. The test may not terminate, might not be a verifiable statement, right? So the statement X, the element is within the set, might not be a verifiable statement, but it's still a statement that is associated with an experimental test. And so the idea that we have this sigma algebra or Borel set, it's required by the fact that we are only interested in statements that have a test associated with it. And so from the physical side, since we're interested in only that, we don't encounter the paradox.
Okay, thank you. All right. Okay, another question from Catherine. I think this is an intriguing approach, and thank you for the nice talk. I have another question. Sometimes it seems to me that the need in physics precedes the mathematical development. I have in mind constructs such as the Dirac delta function and Feynman measure for path integrals. Perhaps this is too specific for your analysis, or do you have a way of viewing these examples?
So the path integral formulation of field theory is a perfect example of how we have something that is the bond part that we think we need in physics, but the mathematical formulation is such that that formulation doesn't make mathematical sense. And what happens technically is, for people who don't know what the path integral is essentially the idea that you look at all the possible configuration in space and time, and on sets of these things, you conclude something. And to be able to talk about sizes of these sets, again, we need one of these measures that we were talking about before. And what happens is that in the current mathematical specification for these possible evolution of field configuration over time, it can be proven that you kind of have one of these paradoxes, that you can't create a measure that makes sense on this set of subsets. And so from our perspective, that we most likely have the wrong mathematical specification of the problem. And if we have the correct physically motivated specification, we might actually have something that is mathematically consistent. And what happens is very interesting, because we have a colleague for which we are actually writing a paper with that is trying to work on this problem. And mathematicians on one side says, oh, no, it can't be done. And the physicist on the other side is that, well, we don't care. We can just do the calculation. So it doesn't matter that the math is not fixed up. So there is really a problem in trying to do these type of things, trying to get the right mathematical structure, and finding actually people supportive and doing this.
Like the path integral formulation is actually a perfect example of something where we have, as physicists, a prototype theory that we know can be used for many calculations that then agree with the experimental measurements. So we know we're onto something, and the mathematicians have not only not fixed it up, so to speak, tell us that there are really mathematical problems with it, so that they can, tell us exactly what the concerns are from a mathematical perspective. But then, the longer, you want to move forward by creating somehow slightly different mathematical structures that are rigorously mathematically correct, that the mathematicians wouldn't say have issues, have problems, and that of course still work to perform predictions and calculations that agree with experimental measurements. So that's a great example of that.
And to finish on that, remember in the talk we said that these Hilbert spaces contain states with infinite expectation function for observable. It might be that these problems are related, because even there we said, well, we don't really have the correct mathematical definitions.
Do you want to say anything quickly about delta distributions?
Well, I think maybe we should move to another question.
Okay, there are quite a few questions now, and some of them quite long. So we'll take a couple more, and then maybe we'll take the rest offline. So a question from Forrest Stevers. Beginning of the talk, it was said you can't get the answer just by thinking about, which got me thinking. And surprising to me, I don't see the answer to this. Imagine a rocket ship in space. Inside, at the tip of the rocket, there is an object of mass 1 and an object of mass 2 side by side. Now light the rocket, and it goes at constant acceleration, and release both objects. Will they hit the bottom of the rocket ship at the same time? I think not, because of inertia. If so, why is it not the same when dropping objects on Earth?
So if I understood correctly, like once you stop the acceleration, they were during the acceleration they are constrained to accelerate at the same rate, and then you stop the acceleration because you let them go, they will have the same velocity. Yeah. So that they would arrive at the same, if I understand the example correctly.
Yeah, that sounds reasonable to me. All right, there is now a long question from Harold. Maybe we'll take this as the last one. All right, so Harold Wieshammer writes, thank you for this thought-provoking conversation. I would like to have your perspective on two questions. The first one. First, you discuss Galileo's falling bodies as an example of abstract logical reasoning. However, it relies on the intuitive and unjustified assumption that when you couple heavy and light mass, the sum is slowed down. That is not what happens for more or less charged objects in electric fields. Heavier charges are accelerated more, and coupling objects coupling objects makes them drag along smaller charges. Neither does Galileo's argument rule out that heavier bodies fall slower than lighter ones. I posit that both show the fallacy of pure thought arguments. If you want to comment on the first one.
So I'm not an expert in Galilean thinking. There are like philosophers that write paper on all of this with all the things analyzed. I can probably just reference those because I don't think I can become, I haven't thought these things so deeply. Like it's really held as one of those things that it can be given by pure thought. So
electromagnet, I haven't thought about combining charges and electromagnetism. I don't think I'll be able to think on the spot right now, but that is certainly something I'd be interested in thinking about. Thinking about offline.
Sure. Yeah, the second one's a bit more technical. So why don't we leave it there? And so for people who want to hang around and ask the questions that were not asked online here, go ahead and stick around in private, and we'll take those questions. But to everybody else, thank you very much for joining. The next public lecture will be by Emory Brown from MIT, Harvard, Massachusetts General Hospital, who will speak on January 21st, Sunday at 1 p.m. So I'll see you all then. Thank you for coming, and take care. Have a great weekend.